Hi everybody, it's Miss Peachy from your WCA physics class, coming to you for video 2 of the momentum impulse tutorial. So in the previous video we described what momentum was and what impulse or the momentum impulse theorem is. And so now I'm going to work through some practice problems on that, and hopefully they make some sense to you. And if you have questions, of course, feel free to call me or to send me a webmail message. All right, so I'm going to go ahead and direct your attention down to my notebook again. And we'll flip it around and make it bigger. Zoom in. Okay. All right, so we'll start with, I like to look at it as the, I guess there's a couple of different ways you can approach this, and one of them is to look at what force is exerted on something in a collision, because that's important. When people are designing, safety restraints and all sorts of different types of, scenarios, either in maybe amusement park rides or in cars or other types of vehicles, they got to figure out in certain collisions what would be the force that would be imparted to the person whose momentum we're trying to stop. And that force has to be survivable, right? So you have to be able to have such a force that it's not going to be a lethal force. So that's why, these types of math problems are actually really important when they look at engineering and design, when you're looking at different products that are being designed for the consumer. So these types of things are super duper important. So let's look at an example. This is actually given in your text on page 201, and then we'll look at some from practice set B as well. So this is the sample problem. Some has already been done for you, but then we'll look at some from practice set B that have not been done for you. Okay, so this one reads, a 1,400 kilogram car moving westward with a velocity of 15 meters per second collides with a utility pole and is brought to rest in 0.3 seconds. Okay, so we have our utility pole here. That's my utility pole, right? And it's got some wires coming off of it. And then we have a 1,400 kilogram car. Collides with the utility pole. It's apparently can, float in midair as well. Okay, we'll just make this three-dimensional, then you can't say that it's floating. So it's going to collide with the utility pole. It was moving westward with a velocity of 15 meters per second. And the time it takes to come to rest is 0.3 seconds. That's how long it takes to come to rest. Then it says find the force exerted on the car. Now, we're just doing the force exerted on the car. Kind of what I told you before was you have to figure out the force exerted on the person. So there's multiple steps that would involve. You'd have to find the force exerted on the car, and then the car, exerts on the airbag, and the airbag exerts on the person. And so there's, multiple steps involved here. A couple of things to take into consideration here is that this, because it is a vector, we have to establish directionality. And sometimes, we say to the west, to the east, and that works out pretty well. In this particular problem, it's really not a big deal whether or not you are using negative or positive signs. However, if you've got multiple directions, say two things that are colliding and both moving in different directions, it's going to be important to kind of establish positive and negative motion. What I think is the best way to do this is to think of a number line. And a number line has 0 in the middle, and things to the left of the number line are negative, and things to the right of the number line are positive. So then that would also mean that westward is negative and eastward is positive. And I think that's pretty common way to determine the directionality using the negative and positive signs. So we're going to say that this is negative 15 meters per second. Okay. That way we don't have to say to the west, but we can ultimately come back and determine that if it's negative, it's to the west. So we need to know the force that was exerted on this car once it stopped. We know its initial velocity is negative 15 meters per second, and then it stops. So its final velocity is 0. Its mass is 1,400 kilograms. That does not change. And let's see. The time it takes to come to a stop, or delta t, is 0.3 seconds. So it's changed. That's how long it takes to come to a stop. So using the impulse momentum theorem, force times delta t is equal to m v sub f minus m v sub I So in this case, the force is equal to m v sub f minus m v sub I all over delta t. So I'm solving for f. Okay, so m v sub f, the final velocity, is 0. So there's no momentum, right? It has no momentum. So we're just going to get rid of that part of it. So it's just going to be force equals the opposite of m v sub I over delta t, right? Okie dokie. So force would be equal to negative 1,400 kilograms times negative 15 meters per second divided by 0.3 seconds. So let's do a little bit of math, shall we? Clear that off. 1,400 times 15 is 21,000. And so a negative times a negative is a positive, we know. So I'm just going to know that already. Kilogram meters per second divided by 0.3 seconds. Which gives us 70,000. And the units here, kilogram meter per second squared, aka a Newton. Right? Guess what? It's positive. So positive tells me it's to the east. Does it make sense that the force would be applied to the east? Absolutely. If the car is moving to the west, the force to the east is making it stop. It's going to be applied in the opposite direction of the motion to get it to stop. So that gives you a good example of using the impulse momentum theorem to be able to solve for what force is applied to that car, 70,000 newtons. We're going to go to practice problem number 2. This is actually from practice set B on page 201, and it is practice problem number 1 under force and impulse. So on page 201, practice problem number 1. Okay, so the problem reads, a 0.50 kilogram football is thrown with a velocity of 15 meters per second to the right. Stationary receiver catches the ball and brings it to rest in 0.020 seconds. What is the force exerted on the ball by the receiver? So here we have our ball. It is 0.50 kilograms. Our stationary, meaning unmoving, receiver. And he's going to catch it and bring it to rest. So the final velocity of the ball will be 0. The ball has a mass of 0.50 kilograms, and it takes him 0.020 seconds to actually cradle that ball and bring it to rest. So he's going to catch it. Apparently, he's not going to run after the catch. So we want to know the force exerted on the ball. We don't know that information, so we're going to be using the force or impulse momentum theorem, to be able to solve this. Remember, this means that force times delta t is equal to the change in momentum, mvf minus mvi. Just like the previous problem that we did, there is no final momentum because they're not moving. So this one we can kind of get rid of. Also remember that the ball is moving to the right here, so that is kind of our directionality. We're not doing west and east anymore, but we can say that to the right, just like our number line, to the right is positive and to the left is negative. So we're going to call that a positive 15 meters per second. So same kind of solution for the last one, force equals, and then the opposite of MVI divided by delta T. So force is equal to negative 15 meters per second times, what's the mass? 0.50 kilograms divided by 0.020 seconds. And this just becomes a little bit of a plug-and-play math problem at this point. 0.50 times 15, and that's negative. Oh, let's try that one more time because that didn't work. 0.50 times 15. Okay, yeah, it did work. Negative. And then divide that by 0.020, which gives us an answer of 37.5 kilogram meter per second squared, which is a Newton. Okay, so 37.5 newtons. And remember, because this is still negative, I want to forget the negative sign here. Negative means it is to the left. Okay. So again, that kind of gives you an idea. Now, can you see the contrast here of the 37.5 newtons of force that the football player has applied to him versus the 70,000 newtons of force that the car has applied to it? So we can really kind of get an idea of the different types of forces in these particular situations. All right, so there are other problems in here where you're going to have to solve for velocity or solve for change in time. But again, it's just the same kind of situation. Just going to be rearranging the variables and solving for the one you don't know. If you have any questions or concerns, feel free to give me a call at extension 2204. Otherwise, send me a webmail message. Have a fabulous day, everyone.